Welcome to speed up your data science tasks by a factor of 100 plus using Azure ML and NVIDIA Rapids session. This is part of GTC Digital 2020. My name is Tom Drabas and I will be presenting our work today. This material has been prepared jointly with Daniel Schneider and Cody Peterson from Microsoft Azure. Let's start by outlining what we are going to talk about today. First, we'll introduce the Azure ML service. This will be a very brief rundown of the service itself and what it has to offer. Next, since we're talking about speeding up data science workloads, we cannot miss talking about NVIDIA Rapids. We will walk you through the main features. By now, I am pretty certain many of you have already seen more in-depth presentations of this topic, so we will be very brief. Following the Rapids introduction, we will briefly delve into our newest contribution to the DASK community that comes in a form of the Azure MLCluster. The Azure MLCluster allows anyone to quickly and painlessly start DASK clusters on Azure ML and tap into all that the service has to offer. Finally, we will showcase two use cases. First, we will compare speedups one gets from moving from Pandas to cuDF. Second use case is a workload that spans a cluster of multiple multi-GPU nodes. The code for the session is available on my GitHub, so just follow the link below if you want to check that out. Let's begin with introducing the Azure ML service. Azure ML is a compute and framework agnostic service. You can run Python or TensorFlow or PyTorch code locally on your machine, and pretty much the same code can run in the cloud on a distributed cluster, of course assuming that your code allows for such deployment. You can interact with the service via any of the community familiar IDEs like PyCharm or Jupyter. Visual Studio Code also supports a Jupyter-like experience, so you can do your development in VS Code as well. You can even use command line if you choose to. Upon logging to our newest experience, you will be entering what we call the Azure ML workspace. This is home for all things Azure ML, and as you can see, it's organized into three main sections: the authoring tools, the assets, and the management side. Let's quickly walk through each section. In the authoring tab, you have three choices of authoring your workloads. You can access the notebooks, and this subservice allows you to author your code using notebooks as the name suggests. The automated ML is a tool for doing the hands-free, quote, machine learning model estimation. This service handles the whole data science lifecycle up to estimating a model. It handles data cleanup, featureization, train test splitting, model selection, and hyperparameter tuning. The designer part introduces a drag-and-drop-like experience so you can interact with your data in a more visual way. Under the Assets tab, you can register datasets. These can come from either local files, a cloud data store, some web files you found on the internet, or from the Microsoft Open Dataset directory. A nice feature of this subservice is that it supports versioning. So when the underlying data is refreshed, we will version control it and you can use whichever version you like. The Experiments tab is the heart of everything Azure ML. This is where the jobs you submitted, you can control them and monitor them, and then these jobs run on the compute you specify. You can have multiple experiments, like testing SVM versus XGBoost, and within each experiment, you can have multiple runs, where, for example, you test various hyperparameters. Once you're happy with your model, you can stitch the data pre-processing and model inference into a pipeline. The models, just like datasets, maintain versions, so when you can register them with the service. If you do a refresher or retrain your model with other hyperparameters, you can save version 2 or 3 or n or 4 of the model and then use it in your pipeline. The endpoints expose a REST API where you can use the trained model to score a record. Finally, the Manage tab gives you access to the underlying services. Here you can create and delete your compute resources, such as notebook running compute instances and training and inferencing clusters. You can also register data stores like Azure Data Lake or Azure Blob Storage, so you don't have to store the credentials in every single notebook you author. Finally, the data labeling tool helps teams with the mundane task of labeling data. How does this all work? Well, let's have a quick look. In this case, we're looking at the use case where someone submits a job from their own computer. The script gets sent to the Azure ML service. We'll then pick it up and spin up a cluster based on the Docker image you specify. The service also has plenty of curated images you can pick from. The VM gets deployed to the compute target, where we also mount all the data stores or datasets that you specify. The job now runs, and all the logs and other outputs you can track in your notebook via widgets or in the Azure ML workspace through the means of the experiments. But you might be wondering, how does this help a data scientist? Well, as you can see, we streamline the data science DevOps from preparing the data through the experimentation all the way up to the model deployment. All this can be done from the SDK layer, or you can use other authoring tools that we mentioned earlier. And you are, of course, not confined to this linear cycle. With the versioning tools of datasets and models, as well as the built-in experimentation framework, you can work on any of the stages of this process at your will. Now, let's switch gears and talk a bit about NVIDIA Rapids. Rapids sits on top of GPUs. It heavily simplifies a once daunting task of writing your own CUDA kernels, and thanks to the Apache Arrow, it enables massive speedups for data processing tasks. It already has invested into many data science areas like analytics, machine learning, or graphs. It also recently added very powerful visualization capabilities in the form of the cuCross filter. The beauty of Rapids also comes from the fact that you don't really need to learn a completely new API, since most of the APIs in Rapids are modeled after very well-known and popular data science frameworks like Pandas or Scikit-learn on Network X. Your current code base would require minimal to almost no change to run things on a GPU using Rapids. I said none, of course, since you'd have to change the import statements. So this transition is quite simple. Take your Pandas code and change the import to cuDF, or take your Scikit code and use cuML instead. This way, you can scale up your CPU code and execute it on a GPU. If you want to scale out, you can use DASK to either deploy on CPU or GPU clusters. In the second part of the presentation, we will showcase exactly the latter case. Every data science project starts with data. We need to read it, clean it, and make sense out of it. cuDF is a Python library that harnesses the power of GPUs for ETL. As with all things Rapids, cuDF is a Python API that sits on top of libcuDF, that is a mix of CUDA and C++ code. Another cool thing about cuDF is that you can write Python code that will be just-in-time compiled to CUDA kernels using Number. If you check the repo I showed you earlier, you will see the examples of how to do that. cuML is a powerful library that takes the power of Rapids and brings it to the more traditional machine learning. Until Rapids came along, the power of GPUs was mostly reserved to deep learning frameworks. cuML, as I stated earlier, is modeled after Scikit-learn. There are already many models implemented as GPU-enabled equivalents with almost exactly the same interface. We have access to random forests for regression and classification, logistic regression, clustering methods, and so on. My favorite one, UMAP, is also available and it's extremely fast. On top of that, some of the models are already able to take advantage of multi-node, multi-GPU per node clusters. Graphs are present everywhere, and obviously they are also part of Rapids. Some truly impressive speedups can really be found when using cuGraph when compared to Network X. On the model availability side, Rapids offers a plethora of algorithms to solve community problems or analyze components or links. Traversal of the graph, like the single source shortest path or the breadth-first search, is also available. This is the spot where Rapids really shines. Some of the algorithms, like PageRank, used to take hours if not days, and now they take seconds when using GPUs. Finally, if you haven't yet checked out the Rapids website or their documentation, go to the docs.rapids.ai to explore the whole API. Unless you can afford the DGX1 or DGX2 machines from NVIDIA, the biggest problem with current generation of GPUs is their memory size. While the memory is quite abundant for CPUs, GPU's limited memory per single card requires scaling up to multiple GPUs within the same machine or out to multiple machines that are GPU enabled. This is where DASK comes in handy and allows you to take your workloads and distribute them to multiple machines. Being a purely Python framework, DASK's powerful computation engine shines in this setup. Therefore, allow me to introduce you to our newest offering, the Azure MLCluster, that will soon become a part of the DASK Cloud Provider framework. This particular class is the easiest way to start any DASK cluster on Azure, as we do most of the heavy lifting for you. Azure ML, as part of creating the compute targets, allows you to bring your own Docker images and use them to deploy your DASK cluster. This way, we assure that every single node in our cluster has exactly the same configuration, and this also gives you the flexibility to bring any additional modules you wish to include in your setup. Once instantiated, the Azure ML Clusters API, since it is derived from DASK distributed cluster, allows you to scale up and down your resources and turn them down once you're done using your cluster. This scaling can also be done using the interactive widget. In addition, you can instantiate the DASK cluster from either your own machine, and during that process we build an SSH tunnel to the DASK scheduler, the Jupyter and the DASK dashboard processes running on the head node, or you can submit it from a notebook instance running on Azure ML that is within the same VNet. The latter solution simplifies and secures your deployment, so it's definitely recommended. In a slight departure from how DASK creates its clusters, we decided to instantiate a Jupyter lab running on the head node, running along the DASK scheduler. Firstly, we get an additional worker that runs on the same node, since otherwise a VM with, for example, 4 GPUs would simply act as a glorified scheduler, wasting resources. Secondly, if we instantiate the client object on the head node from within the notebook, we are guaranteeing that the whole deployment is homogeneous. Every single worker node and the node running the client have exactly the same configuration in terms of the hardware and the software, since we're using the exactly same Docker image on each node. What is more, we are currently undertaking more work to enable the Kubernetes as the compute backend, so scaling up and down of the clusters is going to be almost instantaneous. Well, you might be now wondering, how can I use it? It is a very simple setup where, in the easiest case, all you need to provide is the workspace, the compute target, and the environment objects. There are of course many more switches you can pull, but at the minimum, this is all you need to get started. This of course will start a CPU cluster, which is not necessarily the topic of this presentation. But as I mentioned earlier, you can scale the cluster up and down programmatically via API or through the widgets, as you can see that on the right-hand side below. And since we're starting the Jupyter Lab process on a remote cluster, we are automatically printing out the link to that running instance so you can get started developing straight away. Of course, the dashboard link is also available right below. But enough of the introductions. Let's check what you can achieve by switching from CPU frameworks like Pandas to running things on GPUs on Azure ML. We run a simple benchmark. First, we read 11 million records and simply process them. This is exactly the first step you take if you receive any data. You read the data and then try to featureize it. In this particular example, we use 1 month's worth of New York Taxi data and run the equivalent workloads on CPU and GPU. The workloads drill down to subsetting the dataset to some useful data by cleaning out the outliers and removing some of the columns we won't need. Next, we do some data featureization, like we process some dates or calculate the distance between 2 points on a plane before sorting the data. Finally, we perform some simple aggregations by grouping by bin first. Nothing here is really something you wouldn't do yourself if you received this data. In our tests, depending on the hardware, we saw speedups of anywhere between 10 to 20 times over CPU when using any regular API from both Pandas or Rapids. However, if you start using some custom kernels, then things start to get even more interesting, as we've seen speedups of over 1,000 times. Overall speedup in this case was almost 100 times over CPU. When you compare the pricing, the average GPU VM would cost anywhere between 8 to 12 times the comparable CPU instance. With 100 times speedup, you're saving a lot of money. If we look closer and compare the runtimes, you can see it takes around 1.5 seconds to read the data on Rapids compared to 18 seconds doing exactly the same thing on a CPU. Overall, the speedup on P40 was hovering around 8 to 20 times until we start using a kernel that casts the fare into an integer. That operation took 2 minutes and 23 seconds on a CPU compared to 0.14 seconds on a GPU. That's right, that's a decimal fraction of a second. And that's over 1,000 times speedup. Overall, it takes 2.5 minutes to read and process 11 million records on a CPU versus only mere 3 seconds on a GPU. When you start approaching 10 times the data size, these differences become even more pronounced. So let's take it up a notch or two. I am showing off here a little bit, but this is exactly one of the clusters that I instantiated on Azure ML a while back. And you are looking here at almost 2.2 terabytes of GPU memory that you can use for whatever workload you want. The example here uses only a fraction of that behemoth. We used 32 V100 GPUs with 16 gigabytes of memory each. But as you can see, scaling the number of records by a factor of 100 times, and scaling out to 32 times the original number of GPUs, we can read over 1 billion of records in around 1 minute and 22 seconds. But things only get better from here. Computing a single thing everyone does when he or she gets their hands on a dataset, the descriptive statistics, takes only 71 seconds. To aggregate 1.1 billion records, it takes only 71 seconds. And that's not the end. Estimating an XGBoost model that predicts the taxi fare on this dataset takes 1 minute, as you can see. We can build an XGBoost model on a 1.1 billion records dataset in 1 minute. And if we don't like it, we can play with the hyperparameters and have another one estimated in the next minute. But we actually like this particular model. We got a model with almost 90% R². So after roughly 3.5 minutes from starting reading the data, we end up with a model with almost 90% R². You can try achieving the same thing on a CPU cluster. So in summary, we hope by now that you have a basic view of the Azure ML service, and I am almost certain by now you know a lot about Rapids, not only from this presentation, but mostly from other ones. We hope you can use the Azure MLCluster at some point in the future to unlock the huge potential dreaming inside GPUs running on Azure ML. My name is Drabas, and it was a pleasure to walk you through this presentation. If you want to stay in touch, follow me on Twitter or ping me on GitHub. Stay safe, everyone.